All that has existed, exists, or will exist in our observable universe: atoms, planets, stars, and galaxies. Not just here, but everywhere. Everything was once concentrated in one spot, packed into a space millions of times smaller than a needle's tip. Your mind screams at you, forcefully rejecting this idea because it seems so insane. And yet this image is probably very close to what reality actually is. Today, we're going to blow our minds by diving into the amazing story of the origin of our universe, while also discovering why the Big Bang has become an almost undeniable reality. This absolutely mind-blowing question is something almost everyone has asked themselves at least once. And to answer it, our cultures and religions have, since the dawn of time, invented cosmogonies, mythological stories that try to explain the birth and existence of the universe. But these stories, entertaining as they may be, are nothing more, in the absence of evidence, than tales born from our imagination. Seriously, answering this riddle has long been out of reach. And then, in the 20th century, with the advent of modern science, things started to change a little. Because we are now able to trace and tell the story of the origin of the universe and its first moments like never before. Sit back, fasten your seatbelt, and get ready to dive into the heart of one of the most baffling phenomena you can find in our universe, since he helped give birth to it and shape it. And what if I don't do too badly? And after we've tied a few carabiner knots in our heads together. Once this video is over, you shouldn't see the universe the same way anymore. But let's start from the beginning. The Big Bang Theory states this happened nearly 13.8 billion years ago. The entirety of the universe that we are able to observe today was contained in a volume of space much smaller than the tip of a needle, where absolutely insane densities prevailed and temperatures reached several billion degrees, before space began to expand to absolutely gigantic proportions. We can agree this statement seems insane. In fact, the first time we come across this theory, if we're sane, our thoughts tend to recoil. It must be said that the idea that the entire observable universe was once confined to a tiny volume of space is what you might call a pretty hard pill to swallow. And when the Big Bang Theory came to the forefront at the beginning of the last century, many scientists considered it completely far-fetched. And if we've come to believe that something so strange really happened, it's because this theory, even though it clashes with common sense as delicately as a hydraulic press, turned out to be the only one able to explain our observations while also being able to precisely describe the state of the early universe. And that's based on extremely solid evidence. Evidence that, written in the sky, has allowed us to trace the history of the origin of our universe, and eventually convince brilliant minds like Soderstein, who at first also found this idea unbelievable. The strongest evidence is found in the universe's movement, and in the discovery that space is expanding. The Big Bang idea started gaining traction among scientists early last century, when, with the development of our telescopes, we realized by observing the great depths of space and studying the galaxies found there, that everywhere we look, no matter which directions of the sky we study, these galaxies are moving away from us at great speed. And they do so even more quickly, the greater the distance that separates them from us. In other words, on the large scales of the cosmos, all the galaxies are moving away from each other, because the space between them has kept increasing over time. This amazing discovery that our universe is expanding is probably so familiar to you now that it may no longer seem surprising. But at the time when these observations were first made, they collided head-on with the most commonly accepted views of the world, with all the delicacy of a sledgehammer. You have to understand that most astronomers at the time thought the universe was static and unchanging, that it had always been that way, that we observe it, and that it would remain so for eternity. Of course, here and there, some stars could be born and others could die. But it was thought then that, in its overwhelming immensity, the universe as a whole had always existed. But the discovery of the recession of galaxies on large scales came to prove to us that we live in a universe that is not static as was long believed, but dynamic and expanding. Now that this idea has taken hold, we will follow its thread and unravel it to the end of its consequences. If the universe is expanding in all directions, and the farther galaxies are from us, the faster they move away, then that means that in the past, they were closer to each other. As the telescope confirms when it scans the deep sky and observes the universe when it was much younger. In the past, there was a time when galaxies were, on a large scale, twice as close as they are now. Another further back when they were 4 times closer, and one even earlier when they were 8 times closer. In short, you get it? We can have fun by rewinding the movie and the universe. Or, more precisely, by shrinking the size of the space that once contained everything we can see today. And by doing so, by rewinding the history of the universe, we see that we gradually go from an immense, cold, and relatively empty cosmos to something surprisingly small, dense, and extremely hot. Because as the distance between the elements decreases, the temperature and the amount of radiation per volume of space only increase. You followed the reasoning so far, but let's go further. By continually reducing the amount of available space, you eventually reach the point where the entire universe is as hot as the surface of a star. And the matter contained within it is so compacted that even light can no longer travel through. Okay, let's pause for just a moment. To think that, in the past, the entirety of our observable universe was hotter than the surface of a star, while being packed into such a tiny volume of space that even light could no longer travel through it, is truly a very strange thought. But what might be even stranger is that if, in extremely ancient times, the universe really did pass through that state, we should be able to find evidence of it. The evidence written in the sky. What happens if, starting from that hot and compact state, we play the film forward in the direction of the expansion of space? Well, the universe, plunged into darkness, expands, it cools down. And suddenly, almost everywhere at the same time, all the light in the world, which was previously trapped, is suddenly free to travel. At this moment, the universe almost instantly shifted from opaque to transparent. It must have been marked by a flash of light that bathed the entire cosmos. And this flash, this burst of light whose existence was predicted by the Big Bang Theory, we eventually found evidence of it. Here is the cosmic microwave background, also sometimes called fossil radiation or cosmic microwave background. This image is of the oldest light in the universe, a light from origins detected by radio telescopes. No matter which direction of the sky we observe, it spreads freely throughout the cosmos. Since the end of the dawn of time, since the moment when light was able to travel through the universe, this image is full of information about the state of our primitive universe. And I won't dwell on it too much, because it deserves a dedicated video all on its own. The thing to remember here is that no matter how you look at the question of its origin, the presence of this radiation at every point in space is almost impossible to explain in any other way than by the fact that the observable universe was, in the past, momentarily found in a state that was extraordinarily smaller, hotter, and denser than it is today. This fossil radiation is one of the strongest pieces of evidence for the Big Bang because it does not rely on equations or models. It jumps out at you. You just have to look at the sky in the radio wave domain for it to hit you. If this radiation is now in wavelengths our eyes can't perceive, if it doesn't make all regions of the cosmos shine brightly, even though it was emitted at a time in history when the universe had the temperature of a fireball, that's because, since it was emitted, it has continued to travel through a space that by expanding cools it down. So, when the universe went from opaque to transparent, the intensity of the radiation that was then free to travel was considerable. And the entire universe was then bathed in a powerful orange glow that slowly darkened, shifted toward red, and eventually moved out of the visible range. After 13.8 billion years traveling through expanding space, the cosmic background radiation has lost much of its brilliance, to the point where its wavelengths have been stretched so much that it now reaches us as a faint, tired radio whisper. And what's even more amazing is that even before it was first detected in the mid-1960s, the properties of this remarkable luminous background noise had been predicted with great precision. That it was both extraordinary and astonishing by the Big Bang Theory, which had anticipated that this radiant and weary light for 13.8 billion years of traveling through an expanding space should today have a temperature of just under minus 170 degrees Celsius. Exactly, the value found for it. By measuring the rates of expansion of space and its age, it was even possible to calculate that this glow from the origins was emitted when the observable universe was barely 380,000 years old. Its diameter was nearly 1,000 times smaller than today. But let's ignore fossil radiation and look even further back in time. We've seen it, but beyond the cosmic microwave background emission, nothing is visible. The universe's first 380,000 years were hidden in darkness. They are hidden from us by matter, which was so dense then that light was essentially trapped inside, except that we can still keep rewinding, as far back as our knowledge of the laws of nature allows us to go, and ask ourselves about the consequences caused by a universe that is ever hotter, ever smaller, ever denser, until a moment, often described as the one that closely follows its birth, when all the matter in the universe is gathered almost in the same place. It's ambitious, but that's our goal. Let's not get ahead of ourselves. Let's pick up our story just before the cosmic background radiation began traveling. The universe was then completely plunged into darkness, and the part we can see today was contained in a volume of space millions of times smaller than what it occupies now. At just 380,000 years old, its temperature matched that of many stars' surfaces. Every point in space is heated to around 2,700 degrees Celsius, a temperature high enough for all the matter in the universe to be in the form of plasma. A soup of protons and electrons with properties that block photons or light particles from passing through. And if we keep rewinding the universe back toward the beginning of time, if the amount of available space keeps shrinking and the temperatures keep rising, within minutes we reach a point in its history, at most a hypothetical moment, a starting point, where the entire universe is subjected to conditions as hellish as those at the heart of stars. And there, you can imagine that if the universe was momentarily and entirely heated to several hundreds of millions, even billions of degrees, during the very first minutes of its existence, it had consequences. Absolutely extraordinary consequences for the cosmos, which the Big Bang Theory is able to predict and explain. And like all exciting ideas, the third proof has to be earned. And you'll see that once you reach its peak and after working your brain a bit, the view is absolutely breathtaking. Don't give up now. First of all, I need to tell you a few words about how matter is made in the universe. Starting with an amazing observation. At the moment I'm speaking to you, there is only one single phenomenon. What in the universe can turn large amounts of atomic elements into others and create new ones? Nuclear fusion occurs at the core of every star in the universe. Because only temperatures of several millions to billions of degrees, combined with extreme density, are capable of destroying certain atoms and creating others that did not exist before. The process of matter becoming more complex in all stars is called stellar nucleosynthesis. This process is why many atomic elements around you and in your body exist. But stellar nucleosynthesis is unable to explain the presence in absolutely staggering quantities of the simplest elements found in the cosmos, such as hydrogen, which makes up nearly 3/4 of the atoms in the universe by mass. But it is not actually produced in stars, which use it, let's say, as a basic element to shine during the first part of their existence. You can see the problem coming. If stars can't form simple atomic elements but make complex ones from them, what created those simple elements? Well, I'll give you a hint. If you have a universe that, for a brief moment, is subjected to conditions similar to those at the core of stars, before abruptly cooling from space's rapid expansion, then you find yourself once the universe has emerged from its state with particles heated to millions or billions of degrees, with a very particular atomic composition, a composition that matches exactly what we observe in the very first stars of the universe. Indeed, when we point our telescopes toward the oldest stars in the cosmos, whose composition is revealed to us by the light that reaches us from them, we find that these are very different from more recent ones, such as our Sun. Formed from clouds of matter ejected by earlier generations of stars, they are enriched with complex atomic elements. And when I say that this process of creating new elements, which took place near the beginning of time, is able to give us, with absolutely staggering and unmatched precision, the composition of the universe at the moment when the very first stars formed. I choose my words carefully. Judge for yourself when we apply the laws of particle physics to an expanding universe, which would have remained for a few minutes in a state similar to what exists at the heart of stars. Before the temperature dropped below the melting point and the formation of new elements, we end up with a cosmos made up of 73.9% hydrogen, which corresponds exactly to the proportions we observe for the most abundant atomic element in the universe. We also end up with a little less than 24% helium, which matches the proportions we observe in the first stars of the universe. Whereas helium is an element that stars absolutely could not have contributed to producing in such proportions, because it takes them staggering amounts of time to even begin forging it. For example, our Sun, which is nearly 5 billion years old, still isn't hot enough at its core to have started forging it. Surprisingly, the Big Bang theory currently predicts this. In nature, 1 out of every 50,000 hydrogen atoms is deuterium, which means its nucleus is slightly heavier because it contains an extra neutron. This matches the observed ratio, 1 in 50,000. That may seem insignificant to you, but it still makes deuterium the 7th most abundant element in the universe. Now, deuterium atoms are among the most fragile and are unable to withstand the conditions. In stars, powerful nuclear reactions destroy them once temperatures exceed 1,000,000 degrees. For them to exist in such proportions, the universe must have necessarily gone through infernal temperatures before suddenly cooling down. And it doesn't stop there. In fact, the proportion of atomic elements like lithium, beryllium, and boron in the universe's first stars, and that we are able to measure by studying the light reaching us, matches almost exactly, down to the decimal point, the values predicted by the Big Bang theory. I don't know if you realize it, but to give you an idea of the feat that was accomplished. It's a bit like, by observing a dish from several meters away and without even tasting or smelling it, being able to precisely deduce its ingredients, the cooking time, the type, and the power of the oven used. 13.8 billion years after the dish came out of the oven. In short, with its ability to explain and predict the composition of the early cosmos with such elegance and efficiency, primordial nucleosynthesis refers to the creation of new elements in the universe's earliest moments. It is the third key piece of evidence supporting the Big Bang theory. And it's amusing to think that all the hydrogen atoms that make up your body and account for nearly 63% of all the atoms found in your body were formed near the beginning of time. In other words, a large part of the matter that is currently in you is almost as old as the cosmos. It was formed when the universe was only a few minutes old at most. I promised you the view would be worth it. And now that we've reached the top, we can resume our dive. Because strangely, we can still keep rewinding the universe, given that the temperature was several billion degrees. That prevailed at the time of primordial nucleosynthesis is still absolutely negligible, compared to the values we are able to reach in our particle accelerators by propelling atomic nuclei at speeds close to the speed of light against each other. Experiments at the Large Hadron Collider let us study matter's behavior when heated to 5.5 trillion degrees, thus reproducing, on a very small scale, conditions similar to those that prevailed during the first millionths of a second after the Big Bang. And to venture beyond the limits of what our physics experiments are able to reproduce and try to go even further back, we have the brains of humans and the theories they've produced which, up until now, have accompanied us and now take over on their own. By working through the equations of theoretical physics, we are able to go back to the prevailing conditions when the universe was barely 10. To the power of minus 30 seconds, everything we see was in a volume the size of a grain of sand. Beyond that point, our grasp of nature's fundamental laws becomes uncertain, and they start to lose their ability to describe what's happening. Until we hit a wall that we've called the Planck wall. By pushing the universe to its limits, going further and further back in time, we eventually reach the point where nothing truly solid exists yet. Our theories suggest nearly all the universe's mass exists as immense energy. When the temperature hits several 100,000 trillion degrees, when the entire observable universe fits into a volume millions of trillions of times smaller than an atom, we find ourselves facing the dizzying Planck wall, which is located precisely at 10 to the power of minus 43 seconds after time zero. And I imagine you're eager to know what's hidden on the other side of the wall. That's true for me and tens of thousands of scientists worldwide. But no one knows, because the Planck wall is simply the moment from which our equations collapse. This wall is a limit, but not the zero instant. And that one, if it even exists, still remains inaccessible today. Theoretical physics is able to describe what happens nearby, but not at the level and even less beyond this boundary, which remains impossible. In fact, when we talk about the Big Bang, we're never really talking about the very first moments of the universe in the strictest sense, because you don't know what happens between hypothetical time zero and that moment, and the instant when the universe was 10 to the power of minus 43 seconds old. When we rewind the history of the universe, as far back as we can go, the tape always stops, inevitably, when the movie had already started. So the Big Bang Theory doesn't really tell us about the birth of the universe, because nothing allows us to say that behind the wall lies its beginning. To know what probably hides on the other side of this curtain, we would need physical theories that don't exist yet. Backed into a corner. Our understanding of the laws of nature, our equations tell us that time and space are not defined. Density and temperature approach infinity, giving rise to what physicists call a singularity, a real headache. So at that level, where all distances theoretically drop to zero, you can lean over the bedside of general relativity, which got burned by coming into conflict with quantum mechanics. Forget everything you thought you knew about reality. Common sense, your brain, beginnings, endings, and even the trash can. And between every word of the previous sentences, you bang your head against the Planck wall while sympathizing with those who work on the subject. And if you find it frustrating not to know what was at the very beginning of the story, you can comfort yourself by marveling that something as tiny as a human brain is made from fundamental particles that were already present at the moment of the Big Bang, and through sheer willpower managed to go back that far. Despite the presence of this wall, which in itself is just a kind of boundary marking the limits of our knowledge, birth, just as astonishing. And even though the Big Bang Theory seems counterintuitive, all observations made so far support it and prove to us that the universe went through an extraordinarily hot and dense state. And I have to say, I like that after decades of evidence, the Big Bang is now unanimously accepted by scientists, while the implausible side of this theory made it difficult to accept for a while. The moral of this story is that nature, with a capital N, the universe if you prefer, doesn't care about what we think is true. The hardest ideas to accept are often the most delightful. And now, allow me to open a very small parenthesis. I can already see comments blooming under this video, often written before even watching it, like, yeah, but it's just a theory. In science, though, theory doesn't mean what most people think it does. It's a system of hypotheses that are consistent with each other, a set of verified knowledge and logical rules that work together to explain what we observe. So the theory of general relativity, the theory of evolution, or the Big Bang are among the most robust systems of thought ever produced by the human mind. Decades of experiments and observations have tested them, and they are able to account for practically everything we observe in their respective fields. And if you want to shake them, you're going to have to go a bit further than a comment under a YouTube video. There are also many other observational pieces of evidence related to large-scale cosmic structures and particle physics beyond those I mentioned. If you're interested, check out Jean-Pierre Illuminet's works. One last thing in this episode, I deliberately took a few shortcuts and allowed myself some poetic license. Old habits die hard. And hoping for forgiveness. In an upcoming video, we'll tackle the misconceptions that almost always surround our image of the beginning of time. I'll show you that beyond the evidence, the Big Bang story is likely even more astonishing than you think. Until then, the universe thanks you for dedicating more than half an hour of your life to the very first moment of its long existence. You can now close the internet and jump out the window, or maybe it's the other way around. And before you end up hitting the ground, remember to subscribe if you haven't already, to activate the bell, and if you feel like it, to support this channel on Typee,